So let's assume we are given a data matrix where each column is a feature, F1, F2, so on and so forth, Fj, so on and so forth, Fd, and each row corresponds to a point, ith point, so on and so forth, n. This is n cross d, and the ith data point is xi transpose here, right? And this is the jth column, right? This is the jth feature or column. Okay, this corresponds columns. This is our standard practice of representing a data matrix. Now, so each of your xi's belong to Rd. Let's assume let xi's belong to Rd, right? So what if I compute a mean vector as follows? Okay, what if, so suppose if I have two vectors, let's call them x1 and x2. Okay, if this is 2.2 and 4.2, this is 1.2 and let's say 3.2. These are two-dimensional vectors. Here x1 belongs to R2, this also belongs to R2. So x1 plus x2 is basically you do component-wise sum. This is your first feature or first component, this is your second feature, second component, right? So you sum these two, that's what it means, which is 3.4 if you sum these two. If you sum these two, it is 7.4. This is what sum of two vectors mean. Okay, this is the sum of two vectors. This is component-wise sum. So mean of vectors, suppose what if I compute x bar, which again belongs to Rd. Okay, where I define my x bar as 1 by n summation over all the points xi. Here xi is a vector, remember. So what am I doing? I'm doing component-wise sum and I'm taking the average. Right? This is what is called a mean vector of a data set. This is called a mean vector. Okay, what am I doing? This is nothing but 1 by n. Okay, x1 plus x2, so on so forth, xn. This is what it means, right? Again, here each of your xi's again belong to Rd. These are not scalars. These are vectors. So just like scalar mean, I can also define a mean vector. Now you might ask, what does it mean geometrically? So let's understand the geometric interpretation of a mean vector. Imagine if I have two features. Again, we'll always understand it in two dimensions, f1 and f2. Let's assume each of them are my points. Okay, just for simplicity, let's assume these are heights of students and these are weights of students, just for simplicity. So each of our xi belongs to R2. Okay, where the first one is height, the second one is weight. Okay, the first feature is height, this is my f1, this is my f2. Okay, so what does mean vector represent geometrically? Geometrically, what it represents is nothing but so this will be your mean vector. Because what are you doing? So if I project all of these points and compute their f1 or feature 1 values, for this you'll have this value, for this you'll have this value, for this you'll have this value. So if I project all of these points on x-axis, okay, now I have scalars, right? I have basically heights of students, and if I compute the mean height, okay, for the mean vector, okay, so for the mean vector x bar, okay, let's call the height of mean vector and the weight corresponding to mean vector. Okay, the height corresponding to the mean vector is nothing but the mean height, the mean of each of the heights of I going from 1 to n. Okay, the mean weight vector corresponding to this is nothing but simply the mean of your wi's I going from 1 to n. Because what are we doing? Let's look at the formula. It's component-wise sum, right? Sum basically is component-wise, which means if I sum all of them and take the mean, I would get it. So geometrically, a mean vector is just like for scalars, right? For scalars, what does mean represent? So for example, for all these values, let's assume the mean is here. Mean is sort of like a central height or the central value, right? Mean is like a central value. We saw median also, if you recall, in exploratory data analysis. But mean, assuming there are no outliers and all of that stuff, mean height represents a central value, and this will correspond to the mean vector, and this is your mean. So this will be your mean weight, and this will be your mean height. So geometrically speaking, if I have a bunch of points like this, right, the mean vector is sort of like a central vector or a central data point, right? So geometrically, mean vector is nothing but a central vector. Just like mean is a central value for scalars, a mean vector is a central value or a central vector. Okay, so that's the interpretation of a mean vector. We'll also see other things like covariance of a data matrix and things like that later in this section.